So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be generalizing the Fresnel integral. You know what Fresnel integral is? It is the integral from 0 to infinity of sine of x squared dx, and that too it is also equivalent to the integral from 0 to infinity of cosine of x squared dx. And we'll not talk about the result here, but we'll talk about it in after the proof, after the generalization, right? So yeah, it's going to be an interesting video obviously. So actually the tools that I'm going to use in this video are these two integrals, right? And don't worry, I have proved those two tools as well recently, so you can consider watching that video as well. Actually, I have proved these two integrals in the same video, actually in a single video. So I'll paste the link of that video in the description box of this video, don't worry about that. But let's just talk about this. But before coming to this and these two integrals, we just have to play around a little bit with these two integrals possibly. Okay, so now let's just taking one of these, let's say the first one, right? So let's just talk about that, and then obviously, and you know what? I have let me just write that down. Maybe you cannot. So the integral from 0 to infinity of sine of bx over x to the p dx, and this is being evaluated to pi times b to the p minus 1 over 2 times gamma of p sine of p pi over 2. So this is the generalization actually. And guess what? This integral is the Dirichlet integral when we plug b equals p equals 1, and that's gonna give us pi over 2. Well, we'll not talk about that in this video because we have already talked about that, but let's just play around a little bit with this. So let's just plug b equals 1 here. So when we plug b equals 1, so this is gonna be integral from 0 to infinity of sine of x over x to the p, right? Yeah, and dx. And on the right hand side, we would be getting rid of this b to the p minus 1 because b is 1, right? So 1 to the p minus 1 is just 1. So we are having pi over 2 times gamma of p times sine of p pi over 2. Okay. And we can write this integral as integral from 0 to infinity of sine of x to the minus p dx, right? Okay. And here, let me just talk about this over here. Okay, we know that Euler's reflection formula. Yeah, I have proved a couple of times this formula, right, in my previous videos. So basically, this says gamma of z times gamma of 1 minus z is pi over sine pi z. Oh, I'm sorry, pi z. So this is the Euler's reflection formula, right? And now I'm just going to isolate gamma of p actually. So gamma of p can be isolated as pi over gamma of 1 minus p and sine of p pi, right? And guess what? Again, we know that we know the double angle formula, and I have proved this also. I have proved this as well in my previous videos, and I have proved using the Euler's formula. So that's quite amazing. So this is 2 sine theta times cosine theta, right? So if we plug if I plug 2 theta equals p pi, so theta is gonna be p pi over 2. So basically, the sine of p pi can also be written as 2 times sine of p pi over 2 and cosine of p pi over 2. Right? Let me just check whether you guys can see all the stuffs clearly. And I think, yeah, it's perfect. So yeah, we can write this as something sort of. Right, so I'm just gonna plug this back over here. So we are gonna have pi over gamma of 1 minus p times 2 times sine of p pi over 2 times cosine of p pi over 2. I hope you guys are clear with that. And let me just check another time. Actually, yeah, it's pretty fine. Okay, so basically gamma of p can be represented as pi over gamma of 1 minus p times 2 times sine of p pi over 2 times cosine of p pi over 2, right? Yeah, so basically I'm just going to replace this gamma of p with this big chunk of things. So basically we have pi in the numerator actually and 2 times that thing actually. So it's pi and it's gamma of 1 minus p 2 times sine of p pi over 2 cosine of p pi over 2, and we are having sine pi over 2 as well here. So, I'm sorry, sine p pi over 2. Okay, so now we are just gonna having some sort of good cancellations here. This pi, this 2, and this sine pi p pi over 2 and sine p pi over 2 as well. And this is gonna be in the numerator actually. So basically, I think I'm gonna erase some stuffs, or let me just write that down here. So our integral from 0 to infinity of sine of x to the minus p dx equals gamma of 1 minus p and times cosine of p pi over 2. Isn't that amazing? Okay, so we just got the first thing that we demand for in order to just talk about the Fresnel integral. And now let's just talk about the second tool. Let's just use that as well. So the second tool says integral from 0 to infinity of cosine of bx over x to the p dx, right? And again we're just gonna plug b equals 1. So basically it's gamma of 1 minus p sine of p pi over 2 over b to the 1 minus b to the p minus 1 minus p. So for b equals 1, integral from 0 to infinity of cosine of cosine of x only and x to the minus p dx equals gamma of 1 minus p and sine of p pi over 2. And do you remember, guys, I have used these two integrals in the proof of the Kumar series actually. And I just promised you guys that I'm just gonna bring the proof of these two integrals as well, and here it is. And I'm not talking about an individual video to prove these two integrals down, but we are just gonna play around furthermore in this and just to reach up to the Fresnel integral, right? Okay, so yeah, these two results that we have got from our proved results that we have proved recently, right? And now let's just talk about the Fresnel integral. Okay, I'm sorry, the generalization of the Fresnel integral. So basically, we have to talk about the integral I, which says integral from 0 to infinity of sine of x to the, let's say, you can plug, yeah, look, it's bx, the argument is bx, but if we're going to talk about the Fresnel integral, so we have to talk about x to the b and over x to the p dx. So this is what we are going to talk about. And the Fresnel integral is just when you plug b equals 2 and p equals 1. Oh my goodness, I think I should replace this p and b because they're quite confusing, I think. And let's say this is a and this is z. So when you plug z equals 2 and a equals 0, so you're gonna have the Fresnel integral, right? So yeah, let's just generalize that. Okay. So yeah, we have to talk about this, right? Okay. So basically, from this result, actually this very result, yeah, we have x only. So we just have to get rid of these z exponents over there. So let's just plug x to the z is t, right? And from here we can say x is t to the 1 over z. And if we talk about the derivative, so it's gonna be dx is 1 over z and t to the 1 over z minus 1 dt from this very equation. And the bounds will not change. Bounds ain't gonna bother us because when x is 0, t is also 0, and when x is infinity, t is also infinity, right? Okay. So our I is gonna be integral from 0 to infinity. It's gonna be sine of t, right? And this x is t to the 1 over z. So basically it's t to the 1 over z to the a. And we are having the derivative factor, which is 1 over z t to the 1 over z minus 1 dt. Okay, and let's just play around with this. So I think I just okay, I think I should copy the results that we have got. So basically it's the integral of sine of x to the minus p dx as gamma of 1 minus p cosine of p pi over 2, right? And if we talk about the second one, so it's integral from 0 to infinity of cosine of x to the minus p dx equals gamma of 1 minus p and sine of p pi over 2. Okay, so yeah, now I'm just gonna erase this blackboard. Okay. It's easy, dude. It's easy. It's not difficult. So our I that we are having is integral. Well, we can just factor out that 1 over z because it's a constant. An integral from 0 to infinity of sine of t, and this can be written as t to the negative a over z. T to the negative a over z, and we are having t to the 1 over z minus 1 dt, right? And yeah, we are having that thing. Okay, and now yeah, okay, so basically yeah, this is what we are having now. I equals 1 over z times integral from 0 to infinity sine of t, and this can be written as t to the minus a over z plus 1 over z minus 1 dt. Okay, now let's just talk about the integral that we have proved. So it's the integral from 0 to infinity of sine of x to the minus p dx 1 minus p, and it's cosine of p pi over 2. And if we are gonna replace wait a second, actually I think we should talk about yeah, minus p minus 1. We can just replace it with that, or maybe, look guys, you know what, actually we can plug negative factor. Actually that's a negative, so it's going to be negative over here, so it's negative and that's going to be plus. So this is your p actually, right? This is your p. So in order to do that, we can just directly substitute over that. So basically here in this case, your p is a over z minus 1 over z plus 1. So if we talk about I, so it's 1 over z, and times when you plug p equals it's a over z minus 1 over z plus 1. So it's gamma of 1 minus a over z and minus 1 over z plus 1 and cosine of a over z minus 1 over z plus 1 pi over 2. Okay, right? Yeah, let's just talk about this. Okay, so basically that's what we are having. Okay, so our I is 1 over z, and this we can write this as 1 minus a over z plus 1 over z and minus 1, and we are just getting rid of this minus and plus actually, and we are having cosine of yeah, it's, wait a second, we can write this as a minus, wait a second, it's a minus 1 pi and over z, right, and over 2. Actually it's, look, wait a second, don't get confused, a minus 1 pi over 2z, right, and plus pi over 2, right. Actually I just combine these terms with each other, and then this pi over 2 with another, like, separately. But first of all, let's just talk about cosine of theta plus pi over 2. So from the double angle, like, not actually I have proved this, cosine of a plus b. So cosine of a plus b is cosine of a, cosine of b actually, and minus sine of a, sine of b. So for our case, it's cosine of theta, cosine of pi over 2, and minus sine of theta and sine of pi over 2. So cosine of pi over 2 is 0, and we are having minus sine of theta because sine of pi over 2 is 1. So basically cosine of cosine of theta plus pi over 2 is minus sine of theta. So for our case, theta is this one, right? So it is we are having gamma of 1 over z times gamma of, we can write this as 1 minus a over z, and we are having, wait a second, minus sine of a minus 1 pi over 2 z, right? And yeah, okay, and let me just do a small change actually there. And the change is that we know that sine of minus theta is minus sine theta, so we can consider taking a negative out in the argument of sine, and that's gonna give us I equals 1 over z, gamma of 1 minus a over z, and minus sine of minus 1 minus a pi over 2z. So yeah, finally we are having our generalized Fresnel integral. So I equals 1 over z times gamma of 1 minus a over z, and it's sine of 1 minus a pi over 2z. And here, guys, here is your generalized Fresnel integral. And I think it's been 18 minutes. Okay, yeah, it's good. So yeah, basically this is what we're having. And now let's just talk about when we plug where was it? So we had to plug, actually we were having integral I as integral from 0 to infinity x to the z, and it was x to the, wait a second, it was x to the a and the denominator. So we have to plug a equals 0. So we're gonna have 1 over z times gamma of 1 over z and times sine of 1, yeah, it's 0, so it's pi over 2z. Okay, let's just talk about that. And also we have to plug z equals 2. Wait a second, guys, let me just talk about this. So when we plug here z equals 2 and a equals 0, because that is gonna give us integral from 0 to infinity of sine of x squared dx. So our I is gonna be 1 over 2 times gamma of 1 over 2, and it's sine, and it's gonna be pi over 4. So it's pi over 4. So we know that gamma of 1 over 2 is the square root of pi, and I have proved that. Yeah, it's pretty easy to prove, because it evaluates to, like, it can be proven by the Euler's reflection formula when you plug z equals 1 over 2 actually. So yeah, and it's 1 over 2 times the square root of pi, and sine of pi over 4 is 1 over root 2 actually. Wait a second, is everything alright? Or did I messed up somewhere? Because when you plug 2 here, so it's 0, 1 over 2, right? So it's the square root of pi, and it's 0, so it's 2, and 2 times 2 is 4, so it's sine of pi over 4, which is 1 over root 2. Is this being evaluated to square root of pi over 2 root 2? Oh, wait a second. Yeah, it's perfectly fine, guys. It's perfectly fine actually. Because the Fresnel integral is from negative infinity to infinity, right? And it's sine of x squared dx. And this can be written as 2 times integral from 0 to infinity of sine of x squared dx. And we just got this result as the square root of pi over square root of 2 times 2. So which will be helping us to get cancellations of these 2's. So yeah, here it is, the square root of pi over 2. And here is your Fresnel integrals result, guys. Oh my goodness, like this is integral from negative infinity to infinity of sine of x squared dx is the square root of pi over 2. Like, amazing, guys, like literally amazing, isn't that? Yeah, that's amazing. Okay, now let's just so basically you just have to remember this one, or maybe you can consider multiplying both sides by 2. So the integrals will be from negative infinity to infinity, because the argument is even, so it's not gonna bother us to just write 2 in front, and we have to just change the bounds from 0 to infinity, not from negative infinity to infinity, right? Okay, so yeah, that was amazing. Okay, now let's just talk about the cosine one, right? We did just got the final result for the sine one, and let's just check out for the cosine one. Okay, so yeah, let's just talk about this integral. So integral from 0 to infinity of cosine of x to the z over x to the a dx. So again, we just have to change some stuffs that we have did earlier. So basically we would be having 1 over z integral from 0 to infinity of cosine of t, and it's gonna be t to the it was minus 1 a over z and plus 1 over z minus 1, and if it plugging like negative in front, so that's gonna be plus, and it's dt. So again, if we're just gonna plug p equals this argument over there, so we are having gamma of 1 minus p, so it's 1 minus a over z, and it's plus 1 over z and minus 1, and we are having sine of p pi, which is a over z and minus 1 over z plus 1 actually, and it's pi over 2. So yeah, it's 1 over z gamma of 1 minus a over z. And now let's just talk about this. So sine of theta plus pi over 2 is gonna be sine of theta cosine of pi over 2, right? And it's gonna be cosine of theta actually. It's gonna be cosine of theta. So basically, we are having cosine of a minus 1 and pi over 2z, right? And yeah, we can, because cosine of minus theta is cosine of theta only, so we can finally write this as I equals 1 over z times gamma of 1 minus a over z, and it's cosine of 1 minus a pi over 2z. And again, if we are gonna plug in wait a second, yeah, a equals 0 and z equals 2, so we're gonna have the same result that we had, because we know that sine of pi over 4 is cosine of pi over 4 is 1 over root 2. So let's just take a look at the magic. So it's z is 2, so and gamma of 1 over 2, and it's cosine when a is 0, so it's pi over 4. So basically it is coming out to be the square root of pi over 2 root 2. So if you're going to double the integral, so that's going to give us the square root of pi over 2, and that says, finally, let me just write that down, the final result actually. That's amazing, guys. Like literally, just have fun with this. Okay. So integral from negative infinity to infinity of sine of x squared dx equals integral from negative infinity to infinity of cosine of x squared dx. We just have proved these two integrals are being evaluated to the square root of pi over square root of 2. And this is known as FRESNEL integrals. That was fun, guys, and yeah, that was really amazing. We just did it beautifully and like incredibly. We just used the stuffs that we have proven earlier, and now we are done with the generalization of the FRESNEL integrals, and even we just proved the result. Although I haven't talked about the FRESNEL integral earlier, but well, we can prove these integrals by the Gaussian integral as well. And I think I'm just gonna bring videos over that also. But actually, the first time when I saw these two integrals, so I proved them like using some external helps. I just saw the proof by the Gaussian integral, but not by this. But yeah, we are just diving into it, and yeah, it's amazing. Okay, so yeah, again guys, if you got to learn something out of it, please make sure to like, subscribe and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. I'll be there to reply to your questions. Absolutely, I'll make sure to you don't have any kind of doubt, right? Because it's my duty actually. And just tell me guys, how was all these things actually? Because yeah, actually at a point actually I just got confused. What have I done, dude? I think this is just gonna be waste, but it's not always actually. And yeah, okay guys, goodbye. I hope you just liked it. Goodbye guys, love you, take care, and just learn mathematics, because this is the thing to be learned. And I'm just waiting this video to be 30 minutes actually. 41? Well, let's just talk a little bit out. Okay, so guys, we just proved this one and this one in this video only. with the help of these two integrals which we have proved recently. And these are like, this one is the Dirichlet integral, the generalization of the Dirichlet integral, and we have just generalized the Fresnel integral as well. Just clap, get clap, applaud guys, applaud. Goodbye guys.